Hello there, and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Maybe you've had a long day filled with endless tasks, or perhaps you're simply the kind of person who finds peace in the gentle mysteries of the deep blue sea rather than counting sheep. Either way, tonight's journey is crafted just for you. There's nothing you need to do now but let your shoulders drop, your breathing slow, and your mind drift like a piece of driftwood floating on calm waters. Tonight, we're descending into the ocean's embrace. Not the crashing waves or the dramatic storms you might imagine, but the quiet, profound depths where life moves in slow motion and mysteries unfold in whispers. We'll explore the gentle currents that circle our planet, the ancient creatures that glide through liquid darkness, and the peaceful rhythms that have pulsed beneath the waves for millions of years. If these soothing explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. Now let yourself sink deeper into comfort, and let's begin our slow descent into the ocean's most relaxing secrets. The ocean breathes in a rhythm older than continents. Every day, the sea inhales and exhales in patterns so vast and gentle that we barely notice them. Ocean currents flow like the planet's circulatory system, carrying warm water toward the poles and cool water toward the equator in a dance that has continued for hundreds of millions of years. The Gulf Stream alone moves more water than all the world's rivers combined. Yet it flows with the steady patience of something that has all the time in the world. These currents don't rush or hurry. They simply move, carrying nutrients, warmth, and life across thousands of miles in loops that take years to complete. As you rest tonight, these ancient rivers within the sea continue their eternal circulation, breathing life into every corner of the ocean. Beneath the waves, snow falls upward in slow motion. In the deepest parts of the ocean, tiny particles drift downward like snow in an underwater winter that never ends. This marine snow is made of dead plankton, fragments of algae, and microscopic debris that slowly sinks through the water column. But sometimes, when deep currents stir, this snow reverses direction and floats gently upward, creating an ethereal underwater blizzard. The particles move so slowly that a single flake might take weeks to travel from the seafloor to the surface. It's a silent, graceful dance of matter rising and falling in the liquid darkness. A reminder that even in the deepest places, there is movement, there is life, and there is beauty drifting through the eternal night. The ocean holds sounds from across the world in liquid libraries. Water carries sound much farther than air, and the ocean acts like an enormous acoustic chamber where whispers can travel for thousands of miles. The songs of whales, recorded in one part of the Pacific, can sometimes be heard on the other side of the basin. But it's not just whale songs that the ocean preserves. The gentle creaking of ice, the distant rumble of underwater earthquakes, and even the soft patter of rain on the surface all become part of the sea's vast audio collection. These sounds move through different layers of water at different speeds, creating an underwater symphony that plays continuously in frequencies both above and below human hearing. The ocean remembers every sound, carrying these acoustic memories in its depths like a liquid hard drive of the planet's voice. Underwater meadows sway in currents that change with the moon. Kelp forests and seagrass beds create underwater prairies that move with a grace no terrestrial forest can match. These marine plants bend and flow with tidal currents, their fronds reaching toward filtered sunlight in slow, hypnotic movements. Giant kelp can grow 2 feet in a single day, yet it moves with the patience of something eternal. Schools of fish weave between the swaying stalks like birds through trees, while sea otters float on their backs among the canopy, using the kelp as both anchor and blanket. The entire ecosystem pulses with the rhythm of the tides, expanding and contracting twice each day in a dance choreographed by the moon's gentle pull. The deepest trenches hold water that fell as rain before dinosaurs walked the earth. In the most remote depths of the ocean, in trenches so deep that sunlight has never touched them, water moves in currents so slow that some of it has been circulating for over 1,000 years. This ancient water carries dissolved minerals and gases from a world that existed long before human civilization. It's water that may have fallen as rain on primordial forests, flowed through rivers when continents were arranged differently, and slowly made its way to the bottom of the sea, where it now rests in near-perfect stillness. These deep waters are cold, dense, and patient, holding within them the chemical memory of ancient atmospheres and long-vanished ecosystems. Bioluminescent creatures create living constellations in the liquid night, defying the harsh electrical lights of our world. More than 80% of deep-sea creatures can produce their own light, turning the ocean's depths into a galaxy of living stars. Unlike artificial light, bioluminescence is soft, blue-green, and infinitely gentle. Tiny dinoflagellates spark when disturbed, creating trails of light that follow the movements of fish and marine mammals. Jellyfish pulse with rhythmic glows, their bells contracting and expanding like breathing lanterns. Deep-sea fish carry rows of photophores along their sides, looking like ships with windows lit against the darkness. This living light doesn't burn or heat. It simply glows with the cool radiance of life itself, a reminder that even in the deepest darkness, beauty finds a way to shine. The ocean is a record of Earth's climate, stretching back through geological time. Trapped within the shells of microscopic creatures are the breaths of ancient atmospheres. Buried in layers of seafloor sediment, these tiny fossils tell stories of ice ages and warm periods when palm trees grew in Antarctica. The chemical composition of their shells reveals the temperature and carbon dioxide levels of prehistoric seas, preserving the history of ocean circulation from epochs long past. The deepest parts of the ocean are a living library, written in calcium carbonate and time itself. Thermal hydrothermal vents create oases of life in the abyssal desert, where tectonic plates meet and Earth's interior heat escapes. These underwater geysers spew mineral-rich water that supports entire ecosystems independent of sunlight and photosynthesis. Tube worms as tall as people sway in the currents, their red plumes filtering nutrients from the water. Giant clams nestle between rocky chimneys, while ghostly white crabs scuttle across fields of bacterial mats that carpet the sea floor like living snow. The water here is warm, sometimes approaching the temperature of a hot bath, creating pockets of comfort in the otherwise frigid depths. It's a world that proves life can flourish in the most unlikely places. Coral reefs have existed for millions of years, built patiently, one polyp at a time, across centuries. These are the largest living structures on Earth, created not by human hands, but by tiny creatures no bigger than a pencil eraser. Coral polyps extract calcium carbonate from seawater and slowly construct limestone foundations that become reefs. Each polyp adds its small contribution, and over hundreds or thousands of years, these accumulated efforts create underwater cities that can be seen from space. The Great Barrier Reef began forming over 20 million years ago, built by countless generations working together without plan or blueprint. It's a testament to the power of small, consistent actions repeated over vast spans of time. The reef grows as slowly as your fingernails. Yet IT's patience has created one of the most magnificent structures on our planet. Ocean currents carry messages in bottles across decades and continents. The sea connects distant shores through currents that flow with the reliability of rivers, carrying objects, nutrients, and even living creatures on journeys that span years or decades. A bottle dropped in the North Atlantic might wash up on a European beach 5 years later, having traveled thousands of miles on currents that have followed the same basic patterns for millennia. These oceanic highways don't hurry. They move with the steady persistence of geological time, carrying their cargo at walking speed across vast distances. Scientists have tracked floating instruments for years as they ride these liquid conveyor belts, mapping the ocean's circulation through the patient movement of drifting objects. The twilight zone stretches through an ocean layer where day never truly arrives. Between the sunlit surface and the pitch-black depths lies the ocean's twilight zone, a realm of perpetual dusk where the faintest traces of sunlight create an underwater aurora. This zone, which extends from about 600 to 3,000 feet deep, is home to the largest migration on Earth. Every night, billions of small creatures rise from the depths to feed in the upper waters, then descend again before dawn in a vertical journey that happens twice every day. This migration is so massive that early sonar operators thought they had discovered a false seafloor, not realizing they were detecting the movement of countless living creatures traveling through the liquid twilight. Seamounts create underwater mountains where ancient currents converge. Scattered across the ocean floor like submerged islands, seamounts rise from the abyssal depths to create underwater peaks that disrupt the flow of deep currents. These mountains, many of them extinct volcanoes, force nutrient-rich water upward, creating feeding grounds that attract marine life from across the ocean. Some seamounts host communities of creatures found nowhere else on Earth, isolated populations that have evolved in splendid solitude for millions of years. The currents that swirl around these underwater peaks move slowly but persistently, carrying nutrients and plankton in spiraling eddies that can last for months. Each seamount is an oasis in the deep desert of the abyssal plain, a place where life gathers in the slow dance of deep-sea currents. The ocean's memory spans millions of years in layers of sediment that accumulate grain by grain. On the seafloor, far from the turbulence of surface waves, sediments settle with the gentleness of falling leaves. Each layer tells a story of the world above, preserving pollen from ancient forests, volcanic ash from eruptions that happened when continents were young, and the shells of creatures that lived and died in seas warmed by different suns. These sedimentary archives accumulate so slowly that a single inch might represent thousands of years of Earth's history. Core samples pulled from the deep ocean floor reveal ice ages and warm periods, mass extinctions and recoveries, all written in the patient language of settling particles. The ocean floor is a vast library where time is measured not in pages but in microscopic layers, each one a whisper from the distant past. Deep ocean basins hold water so still that it moves like liquid glass. In the deepest parts of the sea, where pressure reaches crushing extremes and temperatures hover just above freezing, water moves with an almost geological slowness. These abyssal waters flow in currents so gentle that a particle might drift for decades without reaching the surface. The water here is incredibly clear, cleaner than the purest distilled water, filtered through thousands of miles of ocean and thousands of years of circulation. This deep water carries no storms, knows no waves, and experiences no seasons. It exists in a state of profound calm, a liquid meditation that has continued unchanged while mountains rose and fell on the continents above. Hydrothermal vents pulse with the planet's heartbeat in rhythms that never cease. Deep beneath the waves, where tectonic plates spread apart, the Earth releases its inner heat through underwater geysers that have been flowing for millions of years. These vents don't erupt violently like their terrestrial cousins. Instead, they breathe warm, mineral-rich water into the cold depths with a steady, rhythmic pulse. The water emerges at temperatures that would scald on land, but in the crushing depths, it creates gentle plumes that rise and dissipate like underwater smoke. Around these warm oases, life gathers in communities that have never known sunlight, sustained entirely by the Earth's internal energy. The vents pulse and flow with the slow breathing of the planet itself, a reminder that even in the deepest darkness, the Earth continues to nurture life. Whale falls create underwater forests that bloom for decades in the deep. When a great whale dies and sinks to the ocean floor, it becomes an oasis of life in the nutrient-poor depths. The whale's body, rich in fats and proteins, sustains entire ecosystems for decades as different communities of creatures take turns feeding on this bounty from above. First come the mobile scavengers, hagfish and sleeper sharks that strip away the soft tissues with patient efficiency. Then arrive the polychaete worms, boring into bones and creating underwater gardens of feeding tubes that wave like flowers in the gentle currents. Finally, bacteria break down the whale's skeleton, releasing chemicals that support unique communities found nowhere else in the ocean. A single whale fall can sustain life for 50 years or more, a slow-motion bloom in the desert of the deep sea. The ocean's surface tension creates an invisible ceiling that supports entire ecosystems. At the boundary between water and air exists a thin membrane invisible to the naked eye, but strong enough to support communities of creatures that live their entire lives upside down beneath the surface. This Newston layer teems with microscopic life that clings to the underside of the sea's ceiling, feeding on nutrients that concentrate at this boundary. Water striders dance across the surface tension, their feet creating dimples but never breaking through. Even larger creatures like sea turtles and marine iguanas use this invisible barrier, pressing their nostrils against it to breathe while their bodies remain submerged. The surface tension acts like a gentle membrane, permeable to gases but strong enough to create a unique habitat where water meets sky. Ancient coral reefs hold libraries of climate data in their limestone skeletons. As coral polyps build their calcium carbonate homes, they record the temperature and chemistry of the water around them in bands of growth as regular as tree rings. These living archives preserve records of ocean temperatures, storm patterns, and even volcanic eruptions in their skeletal structure. Scientists can read these coral chronicles to understand how the ocean has changed over centuries, finding evidence of El Niño cycles, hurricane seasons, and gradual warming trends written in the slow growth of these patient creatures. Some coral colonies have been growing continuously for over 400 years, their skeletons holding memories of ocean conditions from before the industrial age. Each band of growth, H, is a page in the ocean's autobiography, written in calcium and preserved in living stone. Abyssal plains stretch like underwater prairies across the deepest ocean basins. These vast, flat expanses cover more of Earth's surface than all the continents combined. Yet they remain among the least explored places on our planet. The abyssal plains are carpeted with fine sediment that has settled from above over millions of years, creating a landscape as smooth and featureless as fresh snow. Here, in the eternal darkness, strange creatures glide over the seafloor with ghostly grace. Sea cucumbers plow through the sediment like underwater cattle, while tripod fish stand motionless on elongated fins, waiting for food to drift within reach. The plains are not empty deserts, but subtle ecosystems where life moves at the pace of geological time, patient and persistent in the cold depths. Deep sea trenches create valleys where the ocean touches the Earth's core. The deepest parts of the ocean plunge into trenches that cut through the sea floor like underwater canyons. These abyssal valleys, formed where tectonic plates collide and one slides beneath another, reach depths that dwarf the tallest mountains. The water pressure in these trenches is so immense that it would crush any surface creature instantly. Yet life persists even here. Strange, translucent fish drift through the darkness, their bodies adapted to pressures that would compress steel. Amphipods, tiny shrimp-like creatures, scavenge along the trench floors, feeding on the organic matter that drifts down from the world above. These trenches are Earth's deepest wounds, yet they teem with life that has learned to thrive in conditions more extreme than those found on other planets. The ocean's twilight zone hosts the greatest migration on Earth twice every day. As the sun sets, billions of creatures begin their nightly journey from the deep waters toward the surface, creating a migration so vast it can be detected by sonar from space. Lanternfish, squid, and countless species of zooplankton rise through the water column under cover of darkness, feeding in the nutrient-rich surface waters before retreating to the depths at dawn. This vertical migration happens with clockwork regularity, timed to the rhythm of day and night, season after season, year after year. The creatures don't rush their journey but ascend and descend with the patient persistence of tides, following ancient instincts that guide them through the liquid darkness. Methane seeps on the ocean floor create underwater snow that never melts. In certain parts of the deep sea, methane gas escapes from sediments on the seafloor, creating strange formations that look like underwater snowdrifts. These methane hydrates form when gas combines with water under the extreme pressure and cold of the deep ocean, creating ice-like crystals that don't melt in the frigid depths. Around these seeps, unique communities of life gather, sustained by bacteria that feed on the methane and convert it into energy. Tube worms cluster around the seeps like underwater flowers, their red plumes filtering nutrients from the water. The methane snow creates an alien landscape on the seafloor, a place where ice exists in liquid water and life thrives on gas from the Earth's interior. Ocean gyres spin like enormous slow-motion whirlpools that organize the seas. These massive circular currents, driven by wind and the rotation of the Earth, move water around entire ocean basins in loops that take years to complete. The North Pacific Gyre, the North Atlantic Gyre, and their southern hemisphere counterparts act like enormous stirring spoons, mixing nutrients, heat, and marine life across thousands of miles of open ocean. These gyres don't spin violently like whirlpools in a bathtub. Instead, they rotate with the stately pace of celestial bodies, their movement barely detectable to anything traveling within them. Marine creatures ride these liquid carousels across ocean basins, following currents that have flowed in the same basic patterns for millions of years. The ocean floor spreads apart along underwater mountain ranges that circle the globe. The mid-ocean ridges form the longest mountain chain on Earth, stretching for over 40,000 miles along the seafloor. Here, where tectonic plates slowly pull apart, new ocean floor is born from molten rock that cools and solidifies in the crushing depths. This process happens so gradually that the seafloor spreads at about the same rate that fingernails grow. Yet over millions of years, this patient construction has created entire ocean basins. The ridges are not violent places, but gentle workshops where the Earth quietly builds new seafloor, grain by grain, layer by layer, in a construction project that has continued for billions of years. Underwater rivers flow along the ocean bottom, carrying dense water across vast distances. When particularly cold or salty water sinks toward the seafloor, it flows like a river through the depths, following underwater valleys and canyons for thousands of miles. These deep currents move more slowly than surface rivers, but they carry enormous volumes of water across ocean basins in journeys that can take decades to complete. The Denmark Strait overflow carries cold Arctic water southward along the ocean floor at depths of over 10,000 feet, while the Mediterranean outflow spreads warm, salty water into the Atlantic depths. These underwater rivers are invisible from the surface, but they play crucial roles in global ocean circulation, carrying heat, nutrients, and dissolved gases between different parts of the world's seas. Seamount chains trace the movement of tectonic plates like underwater breadcrumbs across the ocean floor. As oceanic plates drift over stationary hotspots in the Earth's mantle, they create chains of underwater volcanoes that record the direction and speed of plate movement over millions of years. The Hawaiian island chain extends far beyond the visible islands, continuing underwater as the Emperor Seamount Chain, a line of submerged peaks that stretches across the Pacific floor. These seamount chains, are Earth's way of signing its name across the ocean basins, marking the slow dance of continents and sea floor that has shaped our planet's surface for eons. Each seamount in the chain is progressively older as it moves. Pools create underwater timeline written in volcanic underwater lakes rock. B, where different densities of water refuse of Mexico and the Re to mix. In away from the hotspot, creating an in the Gulf parts of the deep sea. Ocean, especially pockets of extremely certain salty water, sit on the seafloor like lakes within the sea. These brine pools are so dense that they remain separate from the surrounding seawater, creating distinct boundaries visible to deep-sea cameras. Fish and other marine creatures can actually swim above these underwater lakes, occasionally diving down to touch the interface between the different water masses. The brine pools are toxic to most marine life, but their edges teem with bacteria and specialized creatures that have adapted to the extreme salinity. These underwater lakes create some of the strangest landscapes in the deep sea, places where water floats on water and liquid boundaries stretch across the seafloor like mirrors in the abyss. The ocean's memory extends back to the formation of the first seas, preserved in the chemistry of the deepest waters. Every drop of seawater carries within it the dissolved remnants of ancient continents, volcanic eruptions, and biological processes that have shaped our planet for billions of years. The salt in the sea comes not just from evaporation, but from the slow weathering of rocks, the outgassing of volcanoes, and the chemical exchanges between water and seafloor that have continued since the oceans first formed. This chemical memory is strongest in the deepest waters, where circulation is slowest and the water has had time to accumulate the dissolved history of geological ages. The ocean doesn't just cover the Earth's surface. It holds within its depths the liquid memory of our planet, net's entire history, dissolved and preserved in the patient chemistry of seawater. Even pressure would crush submarines like tin cans. The ocean floor rises and falls with the gravitational pull of the moon. These movements are measured in mere inches, but they represent the breathing of the Earth itself, as tidal forces flex the seafloor and squeeze water through microscopic cracks in the rock. In the deepest trenches, this gentle flexing creates currents so subtle they can only be detected by the most sensitive instruments. Yet these tiny movements have continued for eons, a slow tidal massage that shapes the deepest parts of our planet's surface. Cold seeps weep minerals from the Earth's interior in processes that unfold over centuries. Unlike the dramatic heat of hydrothermal vents, cold seeps release chemicals into the deep ocean at temperatures barely above freezing. These underwater springs leak methane, hydrogen sulfide, and other compounds through cracks in the seafloor, creating oases of chemical energy in the nutrient-poor depths. The seeps flow so slowly that they might take decades to release what a hydrothermal vent expels in minutes. Around these gentle chemical fountains, communities of bacteria, tube worms, and clams build ecosystems based not on sunlight, but on the slow chemistry of the Earth's interior. The seeps are patient providers, offering their chemical gifts to the deep sea in a process as steady and reliable as the sunrise. For abyssal storms move through the deepest ocean like weather systems in slow motion. Far below the surface turbulence, the deep sea experiences its own form of weather, as masses of dense water collide and mix in underwater storms that can last for months. These deep storms don't create crashing waves or violent winds. Instead, they manifest as swirling currents that spiral through the darkness, mixing different water masses and distributing nutrients across the abyssal plains. Deep-sea instruments have recorded these underwater weather fronts as they pass, bringing changes in temperature and current direction to communities of creatures that live their entire lives in the eternal darkness. The storms move with the unhurried pace of deep-sea life, their effects rippling through the food web over weeks and months. Manganese nodules grow like underwater pearls on the abyssal seafloor. Scattered across the deepest parts of the ocean floor, these dark, round concretions form through a process so slow it defies human comprehension. Layer by microscopic layer, metals precipitate from seawater around tiny nuclei, building potato-sized nodules over millions of years. The nodules grow at a rate measured in millimeters per million years, making them among the slowest forming objects on Earth. They carpet vast areas of the abyssal plains like a harvest of geological patience, each one a testament to the ocean's ability to concentrate rare metals through processes that operate on timescales longer than the evolution of complex life. Underwater avalanches reshape the deep ocean floor in events that echo through the depths. When sediments accumulate too steeply on underwater slopes, they occasionally break loose in turbidity currents that flow down submarine canyons like rivers of liquid mud. These underwater avalanches don't happen quickly like they're instead. They flow mountain counterparts. With the density of wet concrete, carrying sediments hundreds of miles across the abyssal plains over periods of days or weeks. These underwater landslides create some of the largest sediment deposits on Earth, building submarine fans that can cover areas larger than entire countries. Ancient water masses flow through the ocean's depths, like liquid glaciers carrying the memory of polar ice. Water that sank near Antarctica decades ago continues its journey through the world's oceans, flowing northward through deep channels carved in the seafloor. This Antarctic bottom water is so dense and cold that it hugs the ocean floor as it travels, carrying with it dissolved gases and nutrients from the Southern Ocean. The water moves at speeds measured in inches per hour, but its journey spans continents and decades. By the time this water reaches the northern basins of the Atlantic and Pacific, it may be 50 years old or more. A liquid time capsule carrying the chemical signature of Antarctic seas from generations past. Seamount ecosystems create underwater islands where evolution follows its own path. Isolated peaks rising from the abyssal depths act like islands in a sea of darkness, hosting communities of creatures that have evolved in splendid isolation for millions of years. Each seamount may host species found nowhere else on Earth, creatures that have adapted to the unique conditions of their underwater mountain. The currents that spiral around these peaks create local weather systems that persist for months, bringing nutrients and plankton in predictable patterns that the seamount communities have learned to exploit. These underwater life demonstrate islands of evolution's creativity when given time and isolation, producing creatures as unique and specialized as those found on remote oceanic islands. Benthic boundary layers create invisible highways just above the seafloor, where specialized creatures navigate by touch and chemical cues. In this thin zone where moving water meets the solid bottom, a unique ecosystem thrives in the interface between the liquid and solid worlds. Bottom-dwelling fish glide through this layer like underwater birds, using specialized fins to maintain their position just above the sediment. Crustaceans scuttle along the seafloor, following chemical trails left by other creatures in currents too weak to disperse the signals. This boundary layer is where the ocean floor comes alive. A busy thoroughfare of benthic life moving through darkness with senses humans can barely imagine. Hydrothermal, the chemical signatures of the Earth's interior across. They drift entire ocean basins, with deep ocean currents, creating oscillating currents that pulse through the deep water with periods measured in hours or days. The waves are invisible from the surface, but they create currents that deep-sea creatures have learned to exploit, timing their feeding and reproductive cycles to these deep-sea rhythms that pulse through the darkness with the regularity of a slow heartbeat. Abyssal clay accumulates grain by grain in layers so thin they record individual volcanic eruptions from millions of years ago. In the most remote parts of the deep ocean, far from the influence of continental sediments, clay settles from the water column at rates so slow that a single layer might represent thousands of years of deposition. Within these microscopic layers, scientists can read the history of the Earth's climate, finding evidence of asteroid impacts, volcanic supereruptions, and ice ages preserved in the patient accumulation of particles that drifted down from the surface world. Each grain of clay is a messenger from the past, carrying with it the chemical fingerprint of ancient atmospheres and long-vanished ecosystems. Deep ocean eddies spin like liquid hurricanes that persist for years in the abyssal depths. These rotating masses of water, some hundreds of miles across, drift through the deep sea like underwater weather systems that never reach land. The eddies trap water, nutrients, and marine life within their slowly spinning boundaries, creating mobile ecosystems that travel across ocean basins over periods of months or years. Deep-sea creatures ride within these liquid carousels, their lives shaped by the slow rotation of currents that isolate them from the surrounding waters. The eddies are born from the interaction of deep currents with seafloor topography, spinning off from underwater ridges and seamounts to begin their long journeys through the abyssal darkness. Calcium carbonate compensation depth marks an invisible boundary where shell and skeleton dissolve back into the sea. Below a certain depth in each ocean basin, the water becomes so acidic and cold that calcium carbonate structures simply dissolve. This invisible line, different in each ocean, marks the boundary between preservation and dissolution, between the solid legacy of marine life and its return to liquid solution. Above this line, the seafloor is carpeted with the shells and skeletons of surface-dwelling creatures. Below it, only the most resistant materials survive, creating a stark boundary that can be seen in sediment cores pulled from the deep sea. The compensation depth rises and falls with changes in ocean chemistry, recording shifts in the planet's carbon cycle that have occurred over millions of years. Nepheloid layers create underwater clouds of suspended particles that drift through the deep sea like liquid fog. These turbid layers, dense with fine sediments stirred up from the seafloor, can persist for months as they drift with deep ocean currents. The particles within these underwater clouds scatter light from deep-sea instruments, creating an ethereal glow in the darkness that resembles moonlight filtering through fog. Marine life gathers at the boundaries of these nepheloid layers, where the suspended particles concentrate nutrients and organic matter. The clouds drift silently through the abyss, carrying with them communities of filter-feeding creatures that have adapted to life in this underwater haze. Thermohaline circulation drives a global conveyor belt of deep water that connects all the world's oceans in a single planet-spanning current. This deep circulation, driven by differences in temperature and salinity, moves water through the ocean basins in a journey that takes over 1,000 years to complete. Water sinks in the polar regions and spreads through ocean, gradually the deep warming and rising as it travels toward the tropics. This deep conveyor belt carries oxygen to the deepest parts of the sea to the surface, connecting and nutrients from the depths, polar and tropical seas in a circulation pattern that helps regulate the planet's climate. The conveyor moves with the patience of geological processes, but its influence reaches every corner of the worldy skyscrapers built from minerals chimneys grow like underwater oceans. Hydrothermal vent precipitating out of superheated water. As hot, mineral-laden water meets the cold, deep sea, dissolved metals solidify instantly, building towering structures that can grow several feet in a single year. These chimneys are among the fastest-growing geological structures on Earth, yet they build themselves through processes as delicate as crystal formation. The chimneys constantly reshape themselves as new vents open and old ones become plugged with minerals, creating an ever-changing landscape of underwater spires and towers. Some chimneys reach heights of several stories before toppling under their own weight, their collapse creating new habitats for the communities of life that cluster around these oases of warmth in the cold depths. Submarine canyons carve pathways through the continental shelf like underwater versions of the Grand Canyon, channels that funnel sediments from shallow seas into the abyss. These vast underwater gorges were carved over millions of years by turbidity currents and ancient rivers when sea levels were much lower. Today, they serve as highways for deep currents that carry nutrients and organic matter from the productive continental margins into the nutrient-starved depths. The walls of these canyons are lined with cold water corals and sponge gardens that filter plankton from the flowing water, creating vertical ecosystems that stretch from the continental shelf to the abyssal plains. Each canyon is a conduit between the sunlit shallows and the eternal darkness of the deep sea, a pathway that connects two entirely different worlds. Ancient methane locked in seafloor sediments creates underwater ice that burns when brought to the surface. These methane hydrates, also called fire ice, form when natural gas combines with water under the extreme pressure and cold of the deep ocean floor. Vast deposits of these crystalline structures lie buried beneath sediments around the world, storing oil and gas reserves combined. The more energy than all known hydrates remain stable only under deep-sea conditions, instantly decomposing into gas and water when the pressure decreases or temperature rises. Around natural seeps where these hydrates break down, specialized communities of bacteria and tube worms thrive on the released methane, creating oases of life powered by ancient organic matter trapped within the Earth's frozen breath. Deep-sea mushroom forests grow in the darkness where glass sponges build underwater cathedrals from spun silica. These ancient creatures, some over 10,000 years old, construct their skeletons from the same material as window glass, creating delicate, translucent structures that filter water with microscopic precision. The sponge gardens can cover acres of seafloor, their glass spicules forming intricate networks that provide shelter for countless smaller creatures. Some glass sponges grow in formations that resemble underwater trees, their branching structures reaching toward currents that bring them the microscopic food they filter from the water. These living glass forests exist in a realm where time moves differently, where growth is measured in decades and patience becomes the ultimate survival strategy. Abyssal storms stir the deepest waters in weather patterns that last for seasons rather than days. These underwater tempests form when different water masses collide deep beneath the surface, creating spiraling currents that can persist for months as they drift across the ocean floor. The storms don't bring rain or lightning, but they redistribute nutrients and heat through the deep sea in ways that affect entire ecosystems. Deep-sea creatures have learned to time their reproduction and feeding to these slow-motion weather patterns, following the stirring of nutrients that these abyssal storms bring to the otherwise stable depths. The storms move with the unhurried pace of everything in the deep sea, their effects rippling through food webs over timescales that dwarf the brief tempests of the surface world. Polymetallic crusts paint the walls of seamounts with layers of precious metals that accumulate over millions of years. These mineral coatings grow on underwater mountains like underwater rust, depositing platinum, gold, and rare earth elements from seawater in crusts that can be several inches thick. The metals precipitate so slowly that the crusts grow at rates measured in millimeters per million years, making them among the most patient geological processes on Earth. Each layer records changes in ocean chemistry over vast periods of time, preserving evidence of ancient volcanic eruptions, asteroid impacts, and shifts in global climate within their metallic bands. The seamounts become underwater treasure houses, their slopes painted with precious metals extracted from the sea by processes that operate on timescales longer than the evolution of complex life. Deep-sea wood falls create underwater forests where sunken logs become islands of life in the desert of the abyss. When trees wash into the ocean and sink to the deep-sea floor, they become oases of organic carbon in the nutrient-poor depths. These wooden islands support unique communities of wood-boring mollusks, bacteria, and other creatures that have evolved specifically to exploit this rare source of terrestrial carbon in the deep sea. The wood can sustain these communities for decades as different species take turns breaking down the cellulose and lignin, creating a succession of life that mirrors the process of forest decay on land. Some deep-sea creatures depend entirely on these occasional gifts from the surface world, their entire life cycles timed to the rare arrival of sunken wood in the eternal darkness. Benthic boundary currents flow like invisible rivers just above the seafloor, carrying nutrients and larvae across entire ocean basins. These near-bottom currents move with such consistency that deep-sea creatures use them as highways, following the flow of water that brings food and connects distant populations. The currents are shaped by the topography of the seafloor, channeled through valleys and deflected around seamounts in patterns that have remained stable for thousands of years. Bottom-dwelling fish ride these currents like birds riding air thermals, conserving energy as they travel between feeding grounds that may be separated by hundreds of miles. The boundary currents are the bloodstream of the deep sea, circulating life and nutrients through regions that would otherwise remain isolated in the vast darkness. Submarine landslides reshape underwater mountains in avalanches that can be triggered by earthquakes half a world away. These massive slope failures send millions of tons of sediment cascading down underwater canyons, carving new channels in the seafloor and burying vast areas of the deep ocean under layers of displaced material. The landslides don't happen quickly like their terrestrial counterparts, but flow like dense rivers of mud and rock that can travel for days across the abyssal plains. Deep-sea creatures caught in the path of these underwater avalanches face burial or displacement. But the disturbed sediments also release nutrients that can support blooms of bacterial life for years after the event. The landslides are part of the ocean's way of recycling itself, moving material from the continental margins to the deepest basins in processes that help shape the architecture of the seafloor. Chemosynthetic gardens bloom around underwater springs, where bacteria convert dissolved chemicals into food without any need for sunlight. These bacterial mats carpet the seafloor around cold seeps and hydrothermal vents, creating underwater meadows that wave gently in the deep currents. The bacteria don't photosynthesize like plants, but instead derive energy from hydrogen sulfide, methane, and other chemicals that seep from the Earth's interior. These microbial gardens form the foundation of entire food webs in the deep sea, supporting communities of grazing amphipods, filter-feeding tube worms, and predatory fish that have never known the energy of the sun. The gardens can cover acres of seafloor with living carpets that process the Earth's chemical exhalations into food, creating oases of productivity in the otherwise sparse depths. Deep-room core sea mussels create underwater monuments that can live for millennia without ever seeing sunlight. These solitary corals grow as single polyps rather than colonial reefs, building cup-shaped skeletons that can reach the size of dinner plates over centuries of patient growth. Unlike their shallow water relatives, these deep-sea corals have no symbiotic algae to provide energy through photosynthesis. Instead, they catch organic matter that drifts down from the surface waters, filtering plankton and marine snow with their extended tentacles. Some specimens collected from the deep sea have been carbon dated to over 4,000 years old, making them among the longest-lived animals on Earth. These ancient corals stand like underwater tombstones on the abyssal plains, their white skeletons marking time in a world where centuries pass. Ab-like seasoned sisal hills roll across the deepest ocean floor in time. These gentle like underwater sand dunes, frozen rises in the seafloor, typically only a few hundred feet high, are the most common topographic feature on Earth, covering more of the planet's surface than any terrestrial landscape. The hills are created by volcanic activity along mid-ocean ridges, then carried away by seafloor, spreading to create vast fields of rolling topography in the deep ocean basins. Between these hills lie valleys filled with fine sediment that has settled from above over millions of years, creating a softly undulating landscape that stretches to the horizon in every direction. The hills provide subtle variations in current flow and sediment accumulation that create microhabitats for deep-sea life, turning the seemingly uniform abyssal plains into a complex mosaic of ecological niches. Underwater rivers of dense brine flow along the seafloor like liquid mercury, carving channels and creating pools where different layers of water refuse to mix. These hypersaline flows are so dense that they behave more like liquid than the surrounding seawater, flowing downhill under the force of gravity and pooling in depressions on the seafloor. The brine rivers carry dissolved salts and minerals from evaporated lagoons or salt deposits, creating underwater streams that can flow for miles through submarine valleys. Where these rivers meet the normal seawater, they create distinct boundaries visible to deep-sea cameras, interfaces between different densities of water that shimmer like heat mirages in the eternal cold of the depths. Seamount-trapped waves bounce back and forth between underwater peaks like echoes in a liquid cathedral. When deep ocean currents encounter the steep slopes of submarine mountains, they generate internal waves that become trapped between the seafloor and layers of different water density. These waves can persist for weeks or months, bouncing back and forth in the deep water like sound reverberating in an empty hall. The trapped waves create oscillating currents that deep-sea creatures have learned to exploit, timing their feeding and spawning to the rhythmic flow of water that brings plankton and nutrients in predictable pulses. The seamounts become underwater tuning forks, creating musical patterns in the flow of deep currents that resonate through the darkness with the regularity of a slow, liquid heartbeat. Cold seeps weep hydrocarbons from the Earth's interior in processes that create underwater petroleum springs. These seafloor seeps release oil, natural gas, and other organic compounds through cracks in the sediment, forming slicks on the seafloor and feeding specialized communities of bacteria that can metabolize these fossil fuels. The seeps often mark the locations of buried oil and gas deposits, creating windows into the Earth's hydrocarbon reserves that lie beneath the seafloor. Around these underwater oil springs, unique ecosystems develop based entirely on the chemistry of fossil fuels, with bacteria converting petroleum compounds into food that supports tube worms, clams, and other creatures found nowhere else in the ocean. The seeps are ancient and persistent, some having flowed continuously for thousands of years, creating stable oases of chemical energy in the cold depths. Nepheloid layers drift through the deep ocean like underwater dust storms that never settle. These clouds of suspended particles, stirred up from the seafloor by deep currents and storms, can persist for months as they drift through the abyssal darkness. The particles within these underwater dust clouds scatter the light from deep-sea instruments, creating an eerie glow that resembles aurora in the liquid night. Marine life congregates at the edges of these turbid layers, where the suspended sediments trap nutrients and organic matter that would otherwise sink to the seafloor. The nepheloid layers are part of the ocean's way of recycling itself, keeping particles in suspension longer so they can be filtered and processed by deep-sea communities before finally settling into the sediments. Manganese pavements cover vast areas of the abyssal seafloor with natural metal tiles that grow over millions of years. These flat, dark crusts form when metals precipitate directly from seawater onto the seafloor, creating pavements of nearly pure manganese that can extend for miles across the deep ocean bottom. The pavements grow so slowly that they record changes in ocean chemistry over geological timescales, preserving evidence of ice ages, volcanic periods, and mass extinctions in their metallic layers. These metal, deep-sea creatures use pavements as attachment surfaces, with sponges, corals, and other sessile organisms anchoring themselves to the hard substrate in regions where the seafloor is otherwise covered with soft sediment. Acoustic shadows created by seamounts and ridges leave quiet zones in the deep ocean where sound cannot penetrate. These underwater sound shadows form when low-frequency noise from ships, earthquakes, or marine life is blocked by underwater topography, creating regions of acoustic calm in the otherwise noisy depths. Marine mammals and fish may use these quiet zones as refuges from the increasing noise pollution of the modern ocean, gathering in the sound shadows like acoustic oases where communication and echolocation can function without interference. The shadows shift with the seasons as different sound sources become active, creating a changing pattern of noise and quiet that deep-sea creatures must navigate in their underwater world. Hydrothermal plume dispersal creates chemical highways that connect distant vent fields across entire ocean basins. The mineral-rich water that rises from deep-sea vents doesn't simply disappear into the surrounding ocean, but forms distinct plumes that can be traced for hundreds of miles as they spread with deep currents. These chemical contrails carry the signatures of different vent fields, allowing scientists to map the connections between distant hydrothermal systems and track the dispersal of vent larvae across the deep sea floor. Marine life follows these chemical highways like underwater migration routes, using the trace minerals and altered chemistry as navigation aids in the featureless darkness of the abyssal plains. Benthic storms stir the sediment on the ocean floor in underwater tempests that can last for weeks. These deep-sea disturbances are created when powerful currents accelerate along the seafloor, lifting fine particles into suspension and creating turbid clouds that reduce visibility to near zero. The storms don't bring wind or rain, but they redistribute nutrients and organic matter across the abyssal plains, creating patches of disturbed sediment that become feeding grounds for deposit-feeding creatures. Some benthic storms are triggered by the passage of deep eddies or the interaction of currents with seafloor topography, while others may be generated by distant earthquakes that send energy through the solid earth to emerge as water movement on the ocean floor. Bacterial mats weave living carpets across hydrothermal vents in patterns that pulse with the rhythm of chemical tides. These microbial communities create intricate tapestries on the seafloor, their colors shifting from white to orange to deep red as different species of bacteria process the mineral-rich water flowing from the Earth's interior. The mats don't grow randomly, but form complex patterns that optimize their ability to harvest energy from hydrogen sulfide and methane. As the chemistry of the vent water changes with tidal cycles and internal pressure variations, the bacterial communities respond by shifting their metabolic processes, creating waves of color that ripple across the seafloor like slow-motion aurora. These living carpets can cover acres of seafloor around major vent systems, their gentle undulations creating a landscape that breath of the deep earths with the chemical pulse. Deep-sea mushroom gardens bloom in the darkness, where solitary corals build underwater sculptures from pure calcium carbonate. These remarkable creatures, unrelated to the reef-building corals of shallow seas, create cup-shaped skeletons that can grow to the size of serving platters over centuries of patient construction. Each coral polyp lives alone, filtering microscopic food from the water with tentacles that wave like underwater flowers in the gentle deep currents. The mushroom corals prefer the stable temperatures and chemistry of the deep sea, where they can grow undisturbed for millennia. Some specimens recovered from the depths have been carbon dated to over 6,000 years old, making them witnesses to the entire span of recorded human history. Their white skeletons dot the AB, sailplanes like monuments to persistence, proof that beauty can flourish in the most unlikely places. Underwater snow drifts through the deep ocean in seasonal patterns that mirror the productivity of distant surface waters. This marine snow consists of organic particles, dead plankton, and fecal pellets that sink slowly through the water column, creating underwater blizzards that intensify during spring blooms in the surface, waters thousands of feet above. The snow doesn't fall uniformly, but drifts with deep currents, accumulating in underwater valleys and behind seamounts like wind-blown drifts on an alpine sea creature's time landscape. Deep their feeding and reproductive cycles to these seasonal snowfalls, gathering at preferred depths to intercept the organic matter as it sinks toward the seafloor. The particles clump together as they fall, forming larger aggregates that sink more quickly, creating pulses of food that rain down on the deep-sea communities in patterns as regular as seasons on land. Abyssal clay records the history of the solar system in layers so fine they preserve evidence of ancient asteroid impacts and supernovae. In the most remote parts of the deep ocean, where terrestrial reach, clay accumulates grain sediments never by grain from space dust, volcanic ash, and the gradual weathering of the oldest rocks on Earth. Within these microscopic layers, scientists have found elevated levels of rare elements like iridium that mark the boundaries between geological epochs, including the layer that records the asteroid impact that ended the age of dinosaurs. Some clay layers contain isotopes of iron that can only have come from nearby supernovae, stellar explosions that enriched our corner of the galaxy with heavy elements billions of years ago. Each layer is a page in the Earth's autobiography, written in particles so small that millions of years of history can fit within the thickness of a human hair. Methane chimneys grow like underwater towers, where gas seeps through the seafloor in steady streams that have flowed for millennia. These structures, built from calcium carbonate precipitated by methane-eating bacteria, can reach heights of several stories as they slowly accumulate around long-lived seeps. The chimneys don't grow quickly, but add material grain by grain as bacteria convert the seeping gas into solid minerals, creating porous towers that provide habitat for specialized deep-sea communities. Some chimney complexes cover acres of seafloor with limestone spires that rise like underwater cities from the abyssal plains. The methane that feeds their growth comes from deep reservoirs of organic matter buried beneath the seafloor. Ancient biomass slowly decomposing over millions of years and releasing its stored energy as gas that bubbles up through cracks in the sediment. Cold water coral reefs build underwater mountains in the darkness where no photosynthesis has ever occurred. These deep-sea reefs, constructed entirely by filter-feeding corals, can grow to heights rivaling terrestrial skyscrapers over thousands of years of patient accumulation. The corals extract calcium carbonate directly from seawater, building their skeletons without any help from symbiotic algae or sunlight. Instead, they feed on organic matter that drifts down from the productive surface waters, catching plankton and marine snow with their extended tentacles. The largest cold water coral reefs can be seen from space, their white limestone structures creating underwater mountain ranges that provide habitat for thousands of species in the otherwise sparse deep sea. These reefs grow so slowly that individual colonies may be older than the oldest trees on land, their skeletons preserving records of deep-sea conditions across entire geological epochs. Brine pools create underwater lakes where the seafloor becomes a liquid mirror reflecting the strange beauty of the deep. These hypersaline ponds form when concentrated saltwater seeps through the sediments, creating dense brines that remain separate from the surrounding seawater. The interface between the brine and normal seawater acts like a liquid surface, complete with waves and ripples that move in slow motion through the dense medium. Deep swim above these sea creatures can underwater lakes, occasionally diving down to test the strange chemistry of the brine with specialized sensing organs. The edges of these pools teem with bacteria that thrive in the extreme salinity, creating colorful mats that border the dark waters like underwater beaches. Some brine pools are toxic to most marine life, while others support unique communities of salt-loving organisms found nowhere else in the ocean. Seamount ecosystems create underwater islands where evolution writes its own rules in isolation. Each underwater mountain hosts communities of creatures that have been separated from their relatives for millions of years, evolving unique adaptations to life on their particular peak. The currents that swirl around seamounts create local weather patterns that bring nutrients and plankton in predictable cycles, allowing specialized communities to develop around these underwater oases. Many seamounts host endemic species found nowhere else on Earth, creatures that have evolved in the unique conditions of their isolated mountain home. The diversity can be astonishing, with some seamounts supporting more unique species per square mile than tropical rainforests. These underwater islands demonstrate evolution's creativity when given time and isolation, producing creatures as specialized and unique as those found on remote oceanic islands. Hydrothermal vent chimneys sing in frequencies below human hearing as superheated water flows through their mineral structures. The flow of high-temperature water through the frequency vibrations that can be detected by sensitive porous limestone creates low hydrophones, giving each vent field its own acoustic signature. These underwater songs change as the chimneys grow and evolve, their mineral structures acting like organ pipes that resonate with the flow of heated water. Marine life may use these acoustic signatures to navigate in the darkness, following the sound of distant vents across miles of featureless sea floor. The songs are constant but subtle, a deep bass note that pulses through the water with the rhythm of the Earth's internal breathing. Scientists can identify individual vent systems by their unique acoustic fingerprints, each one singing its own deep-sea melody in the eternal darkness. Turbidity currents carve underwater canyons with the persistence of liquid rivers that flow for days across the abyssal plains. These dense flows of sediment-laden water begin on the continental shelf and gather speed as they flow downhill, carving channels in the seafloor that can extend for hundreds of miles into the deep ocean basins. The currents don't rush like mountain streams, but flow with the steady persistence of wet concrete, carrying enormous volumes of sediment from shallow seas to the deepest parts of the ocean. Where these underwater rivers finally lose their energy, they deposit vast fans of sediment that can cover areas larger than entire states. The channels they carve become highways for deep-sea life, creating pathways that connect the productive continental margins with the nutrient-poor abyssal plains. Polymetallic nodule fields carpet the seafloor with natural treasures that grow more slowly than any other objects on Earth. These potato-sized concretions, rich in manganese, nickel, and rare earth elements, accumulate around tiny nuclei over periods measured in millions of years. The nodules grow by precipitating metals directly from seawater, adding layer upon microscopic layer at rates so slow they challenge human comprehension. The nodule fields cover millions of square miles of the deep ocean floor, creating underwater treasure houses where the sea has concentrated rare metals through processes that operate on timescales longer than the evolution of complex life. Abyssal hills create the most common landscape on Earth in rolling topography that covers more of the planet's surface than any terrestrial feature. These gentle rises in the seafloor, typically only a few hundred feet high, are formed by volcanic activity along mid-ocean ridges and then carried away by seafloor spreading to create vast fields of undulating terrain. Between the hills lie valleys filled with fine sediment that has accumulated over millions of years, creating a softly rolling landscape that extends to the horizon in every direction. The hills provide subtle variations in current flow and habitat that support diverse communities of deep-sea life, turning the seemingly uniform abyssal plains into a complex mosaic of ecological niches. This underwater prairie covers more than half of the Earth's surface, yet remains less explored than the surface of Mars. Glass sponge reefs build underwater cathedrals from spun silica that filter the deep ocean with microscopic precision. These ancient creatures construct their skeletons from the same material as window glass, creating delicate, translucent structures that can live for thousands of years while slowly filtering nutrients from the water. The sponges grow in formations that resemble underwater forests, their glass spicules forming intricate networks that provide shelter for countless smaller creatures. Some glass sponge reefs cover acres of seafloor, with structures that tower dozens of feet above the surrounding sediment, creating underwater skyscrapers built entirely from filtered seawater and patience. The sponges grow so slowly that individual specimens may predate human civilization, their glass skeletons standing as monuments to the power of persistence in the deep sea. Chemosynthetic bacteria create underwater gardens where life blooms without any connection to the sun's energy. These microscopic organisms derive their energy from chemical reactions, converting hydrogen sulfide, methane, and other compounds into food through processes that require no light whatsoever. The bacterial gardens can cover acres of seafloor with living carpets that wave gently in the deep currents, their colors shifting from white to yellow to deep red as different species process various chemicals. These microbial meadows form the foundation of entire ecosystems in the communities of grazing deep sea, supporting organisms and filter feeders that have never known the energy of photosynthesis. The gardens are most abundant around hydrothermal vents and cold seeps, where the Earth's interior chemistry provides the raw materials for these alternative forms of life. Seamount-associated eddies spin off from underwater mountains like liquid tornadoes that persist for months in the deep ocean. These rotating masses of water, generated by the interaction of deep currents with steep topography, can trap nutrients and marine life within their slowly spinning boundaries. The eddies drift away from their parent seamounts and travel across ocean basins, carrying with them isolated communities of creatures that may be transported hundreds of miles from their original habitat. Deep-sea animals caught within these liquid carousels find themselves in mobile ecosystems that provide both prison and protection, isolated from the surrounding waters but supplied with concentrated nutrients trapped within the eddy's boundaries. The eddies eventually dissipate, releasing their passengers into new environments where they may establish new populations far from their origins. Benthic boundary layers create invisible highways just above the seafloor, where specialized creatures navigate by chemical trails and pressure waves. This thin zone where moving water meets the solid bottom supports unique communities of organisms adapted to life in the interface between liquid and solid worlds. Bottom-dwelling fish cruise through this layer like underwater aircraft, using specialized fins to maintain their position in the gentle currents that flow along the seafloor. Invertebrates follow chemical highways left by other creatures, tracking scent trails that persist in the stable flow patterns of the boundary layer. This near-bottom ecosystem is where the ocean floor comes alive, a busy thoroughfare of benthic life-moving senses that humans can through darkness guided by barely imagine. Cold seep ecosystems create underwater oases where life thrives on the Earth's ancient breath seeping through cracks in the seafloor. These communities, sustained entirely by chemosynthetic bacteria that feed on methane and hydrogen sulfide, can persist for centuries around long-lived seeps that release hydrocarbons from deep reservoirs. The seeps flow with the patience of geological time, providing steady sources of chemical energy that support tube worms, clams, and bacterial mats in regions where no other food sources exist. Some seep communities are so stable that they develop into complex ecosystems with multiple trophic levels, predators and prey, all ultimately dependent on the slow leak of ancient organic matter from beneath the seafloor. The seeps create stepping stones of life across the otherwise sparse abyssal plains, connected by larvae that drift with deep currents between these widely scattered oases. Underwater landslides reshape the deep ocean floor in slow-motion avalanches that can bury entire ecosystems beneath layers of displaced sediment. These massive slope failures, often triggered by earthquakes or the buildup of unstable sediment deposits, send rivers of mud and debris flowing across the abyssal plains for days or weeks. Deep-sea communities in the path of these underwater avalanches face burial or displacement, but the disturbed sediments also release nutrients that can support blooms of bacterial life for years after the event. The landslides are part of the ocean's way of recycling itself, moving material from the continental margins to the deepest basins in processes that help shape the architecture of the seafloor. Abyssal storms create underwater weather systems that redistribute heat and nutrients through the deepest parts of the ocean. These deep-sea tempests form when different water masses collide beneath the surface, generating rotating currents that can persist for months as they drift across the ocean floor. The storms don't bring lightning or precipitation, but they stir up sediments and mix different layers of water in ways that affect entire ecosystems. Deep-sea creatures have learned to time their activities to these slow-motion weather patterns, following the movement of nutrients and organic matter that the storms bring to otherwise stable environments. The storms move with the unhurried pace of everything in the deep sea, their effects rippling through food webs over timescales that dwarf the brief tempests of the surface world. Manganese crusts paint the walls of seamounts with layers of precious metals that accumulate over geological timescales. These mineral coatings grow on underwater mountains through the direct precipitation of dissolved metals from seawater, creating crusts that can be several inches thick and contain significant concentrations of rare earth elements. The crusts grow at rates measured in millimeters per million years, making them among the slowest forming substances on Earth. Each layer records changes in ocean chemistry over vast periods, preserving evidence of ancient climate shifts and volcanic episodes within their metallic bands. The seamounts become underwater treasure houses, their slopes encrusted with valuable metals extracted from the sea by processes that operate on timescales longer than the evolution of life itself. Nepheloid layers drift through the deep ocean like underwater dust storms that never settle completely. These clouds of suspended particles, stirred up from the seafloor by deep currents and benthic storms, can persist for months as they drift through the abyssal darkness. The particles scatter light from deep-sea instruments, creating an ethereal glow that resembles aurora in the liquid night. Marine life congregates at the boundaries of these turbid layers, where suspended sediments concentrate nutrients and organic matter that would otherwise sink to the seafloor. Hydrothermal contrails that can be traced across entire ocean basins as they spread with deep currents. The mineral-rich water that rises from seafloor vents doesn't simply dissipate, but forms distinct signatures that persist for hundreds of miles as they drift with the deep circulation. These underwater contrails carry dissolved metals and altered chemistry that can be detected by sensitive instruments, allowing scientists to map the connections between distant vent fields and track the dispersal of hydrothermal products across the deep sea floor. Marine life follows these chemical highways like underwater migration routes, using the trace elements as navigation aids in the featureless darkness of the abyssal plains. The plumes create invisible roads through the deep sea, connecting isolated vent communities across vast distances. And so the deep ocean continues its ancient rhythms, breathing through currents that have flowed for millions of years, supporting life in forms we are only beginning to understand. In these deepest waters, time moves differently. Seasons are measured in the slow accumulation of marine snow. Weather systems persist for months. Mountains grow grain by grain over epochs that dwarf human history. As you rest tonight, these profound depths continue their patient work. Bacteria gardens wave in chemical currents. Glass cathedrals filter the darkness. Ancient waters carry messages across ocean basins in journeys measured in decades. The deep sea asks nothing of the surface world, needs no sunlight, follows no human schedule. It simply exists in its own slow rhythm, vast and calm and endlessly patient. In the deepest trenches and on the highest seamounts, in the bacterial gardens and glass forests, the ocean holds its secrets gently, not hiding them, but simply existing at a pace too slow and vast for hurried minds to grasp. The deep sea teaches patience through its very existence, showing us that the most profound processes happen quietly, slowly, and beyond the reach of surface storms. These ancient streams move through abyssal channels carved by turbidity flows that happened when continents were arranged differently on the planet's surface. The water itself may be older than civilizations, having begun its journey in polar seas when glaciers extended far beyond their current boundaries. As it travels through the deep basins, this water carries dissolved minerals and gases that preserve the chemical fingerprints of ancient atmospheres. The deep circulation moves with the patience of geological processes, connecting the memories of different eras in a slow, liquid library that spans millennia. Bacterial chimneys grow like underwater termite mounds, where microbes build limestone towers from pure chemistry. These structures, constructed entirely by colonies of chemosynthetic bacteria, can reach impressive heights as they slowly accumulate calcium carbonate around methane and hydrogen sulfide seeps. The bacteria don't consciously build their towers, but create them as a byproduct of their metabolism, converting seeping gases into solid minerals that gradually form spires and mounds on the seafloor. The chimneys provide vertical habitat in the otherwise flat landscape of the abyssal plains, their porous limestone walls riddled with chambers and passages that shelter specialized communities of deep-sea creatures. Some bacterial chimneys have been growing continuously for thousands of years, their slow construction creating monuments to the power of microbial persistence in the deep sea. Underwater snow machines operate in the deep ocean, where specialized bacteria break down organic matter into particles that drift like gentle precipitation. Decomposers work through the water column. These microscopic tirelessly to process the marine snow that sinks from above, breaking large aggregates into smaller pieces that can be consumed by filter-feeding organisms throughout the deep sea. The bacterial processing creates secondary snowfalls of even finer particles that continue nutrients to the deepest communities sinking toward the seafloor. Carrying. This biological snow machine operates continuously, recycling organic matter through multiple layers of the water column and extending the reach of surface productivity deep into the abyss. The process is so efficient that very little organic matter reaches the seafloor intact, most of it having been processed and reprocessed during its long journey through the darkness. Seamount weather systems create local climates around underwater mountains, where currents generate their own seasonal patterns. These isolated peaks disrupt the flow of deep water, creating upwelling zones that bring nutrients from the depths and generating eddies that can persist for months around the mountain slopes. The currents spiral around seamounts in patterns as predictable as trade winds, creating microclimates that support endemic communities found nowhere else in the ocean. Some seamounts experience regular pulses of nutrient-rich water as deep tides interact with their topography, creating feeding opportunities that deep-sea creatures time their reproduction to exploit. The weather around these underwater mountains operates on its own schedule, independent of surface conditions, but just as regular and reliable as atmospheric weather systems. Abyssal rivers flow along the deepest parts of the ocean floor, carrying cold, dense water through underwater valleys that channel these flows across entire ocean basins. These deep currents follow the topography of the seafloor like terrestrial rivers follow valleys, but they move with the patience of glaciers, their progress measured in inches per hour rather than miles per day. The abyssal rivers transport enormous volumes of water across the deep basins, carrying oxygen from polar regions to the deepest trenches and distributing nutrients across the vast expanses of the ocean floor. Deep-sea creatures gather along the banks of these underwater rivers, taking advantage of the steady flow of food and oxygen that the currents provide. The rivers are invisible from above, but create ribbons of life across the otherwise sparse abyssal plains. Hydrothermal oases bloom and fade across the seafloor as the Earth's internal plumbing shifts and changes over decades and centuries. New vents open when fractures in the seafloor allow heated water to escape, instantly creating oases of warmth and chemical energy in the cold depths. The communities that colonize these new vents arrive as larvae carried by deep currents, settling and growing into complex ecosystems within years of the vent's first emergence. But the oases are temporary, lasting only as long as the geological processes that create them remain active. When vents cool and die, their communities must disperse or perish, their larvae drifting with of chemical energy. This, the currents to find new oases, cycle of birth and death, creates an ever-changing mosaic of life across the deep sea floor. Pressure waves from distant earthquakes travel through the solid earth and emerge as gentle undulations in the deep ocean water. These seismic signals, too subtle for surface dwellers to notice, create slow oscillations in the abyssal waters that can persist for hours after their generating earthquake. Deep-sea creatures may sense these pressure changes through specialized organs that detect minute variations in water density. using them as early warning systems for geological events happening thousands of miles away. The waves propagate through the deep ocean basins like ripples in a vast pond, their passage marked only by the slightest changes in current patterns and water pressure. This underwater seismology connects the deep sea to geological events across the planet, making every earthquake a whispered message carried through liquid rock and water. So cold seep gardens flourish around underwater springs, where ancient organic matter seeps through cracks in the seafloor after millions of years of burial beneath sediment layers. These chemical oases support communities based entirely on the slow decomposition of prehistoric biomass, their energy derived from hydrocarbons that were once living organisms in ancient seas. The seeps flow with such consistency that they create stable ecosystems lasting for centuries, their chemical output as reliable as a heartbeat. Bacterial mats carpet the seafloor around these springs, converting methane and hydrogen sulfide into food that supports tube worms, clams, and specialized fish that have evolved to exploit this unusual energy source. The gardens represent a form of resurrection, where organic matter, buried in geological time, returns to feed new generations of life in the eternal darkness. Underwater dust devils spin through the deep sea as rotating columns of sediment-laden water create tornadoes in the liquid darkness. These benthic whirlwinds form when deep currents interact with irregular seafloor topography, generating spinning flows that lift fine particles high into the water column. The underwater tornadoes move across the abyssal plains like ghostly dancers, their passage marked by trails of suspended sediment that can persist for days after they've passed. Deep-sea creatures caught in these spinning currents may be transported far from their usual habitats, carried along by the rotating water until the tornado finally dissipates. The dust devils are part of the deep sea's weather system, stirring up nutrients and redistributing sediments in patterns that affect entire benthic communities. Bioluminescent snow falls upward in certain regions of the deep ocean, where glowing particles rise rather than sink through the water column. This reverse snowfall occurs when deep currents carry bioluminescent plankton and organic matter upward from the seafloor, creating ascending streams of living light that drift toward the surface like inverted blizzards. The glowing particles trace the movement of deep water as it rises along underwater mountain slopes or through thermal chimneys, painting invisible currents with threads of biological light. Deep-sea predators follow these ascending light trails, using them as highways to reach feeding grounds in the water column above. The upward snow creates temporary galaxies in the liquid darkness, their lights flickering and fading as the organi SMS that produce them live their brief, glowing lives. Methane gardens bloom on the seafloor where gas seeps create underwater meadows of bacterial mats that wave in the deep currents like terrestrial grass. These microbial prairies can extend for acres around major seep sites, their colors shifting from white through yellow to deep orange as different species of bacteria process the seeping methane. The gardens don't grow quickly, but expand slowly over decades as the bacterial communities spread across the seafloor, following the diffuse edges of the methane plumes. Grazing organisms move through these underwater meadows like deep-sea cattle, feeding on the bacterial mats and creating paths that crisscross the gardens. The methane meadows represent some of the most productive ecosystems in the deep sea. Their energy derived entirely from ancient organic matter slowly decomposing beneath the seafloor. Acoustic mirages bend sound waves through the deep ocean, creating underwater illusions where the calls of marine mammals appear to come from directions far from their actual sources. These acoustic distortions occur when sound travels through layers of water with different temperatures and densities, bending the sound waves like light passing through a lens. The mirages can make whale songs seem to originate from empty water, while the actual singers remain hidden behind acoustic shadows created by seamounts or deep currents. Deep-sea creatures that rely on sound for navigation and communication must learn to interpret these underwater illusions, developing sophisticated acoustic processing abilities that allow them to distinguish real sounds from their bent reflections. The ocean becomes a hall of acoustic mirrors, where every sound creates images. See multiple echoes and sediment rivers flow down the slopes of underwater canyons in currents so dense they behave more like liquid landslides than flowing water. These turbidity flows can travel for hundreds of miles across the abyssal plains, carrying enormous loads of particles from the continental margins to the deepest basins. The flows move with the consistency of wet concrete, but with sufficient force to carve channels in the seafloor and transport boulders the size of houses across vast distances. Deep-sea communities in the path of these sediment rivers face periodic burial, but have adapted to these disturbances, with many species capable of rapidly recolonizing areas after turbidity flows pass. The rivers are the deep sea's way of redistributing material across the ocean floor, constantly reshaping the underwater landscape through processes that operate on timescales, both geological and ecological. Thermal stratification in deep ocean trenches creates invisible barriers where different temperature layers refuse to mix despite their proximity. These liquid boundaries can persist for months or years, creating distinct habitats stacked vertically in the deepest parts of the ocean. Each thermal layer supports different communities of organisms adapted to its specific temperature and pressure conditions, creating vertical ecosystems that may be more isolated from each other than communities separated by thousands of miles horizontally. The boundaries between these layers act like liquid membranes, preventing the mixing of water masses and maintaining the distinct characteristics of each stratum. Deep-sea creatures must migrate vertically to move between these thermal zones, crossing invisible barriers that are as real as any physical obstacle. Underwater aurora form in the deep sea when bioluminescent organisms create cascading displays of living light that ripple across the seafloor like liquid northern lights. These biological light shows occur when disturbances trigger mass bioluminescent responses in deep-sea communities, creating waves of blue-green illumination that spread across acres of ocean floor. The displays can last for hours as the luminescent signals propagate through bacterial mats and colonial organisms, each flash triggering responses in neighboring communities. The underwater aurora serve as communication, the darkness. The light networks, allowing deep-sea organisms to coordinate their activities across vast distances in shows are visible only to creatures with eyes adapted to the deep sea's faint illumination, creating a hidden world of biological fireworks in the eternal night. Glass gardens grow on the walls of underwater canyons, where silica-secreting organisms build delicate structures that filter nutrients from the flowing water. These communities of glass sponges, diatoms, and radiolarians create intricate sculptures that can cover canyon walls for miles. Their translucent skeletons forming lacework patterns that catch and concentrate organic particles drifting with the currents. The glass gardens grow with infinite patience, adding microscopic layers to their silicate structures over periods measured in centuries. Each garden is unique, its architecture shaped by the local current patterns and the species composition of its builders. The structures are incredibly fragile, easily damaged by disturbances, yet they persist in the stable environment of the deep canyons where currents flow with predictable gentleness. Chemosynthetic forests flourish around underwater volcanoes, where the Earth's internal chemistry creates groves of tube worms that grow like trees in the mineral-rich water. These forests can cover acres of seafloor with organisms that reach heights of several meters, their red plumes filtering nutrients from the volcanic springs with the efficiency of terrestrial leaves capturing sunlight. The tube worm forests create complex three-dimensional habitats that support diverse communities of smaller organisms, their trunks and branches providing attachment sites and shelter in the otherwise flat landscape of the deep sea. The forests grow and change over decades as new vents open and old ones cool, creating a dynamic landscape where entire groves can appear and disappear within a human lifetime. Deep-sea mushroom farms operate where specialized fungi break down organic matter on the seafloor, creating networks of underground mycelium that process nutrients and distribute them to other organisms. These fungal communities form partnerships with deep-sea plants and animals, trading processed nutrients for protection and organic matter in relationships that mirror terrestrial forest ecosystems. The fungi grow slowly but persistently through the sediment layers, their thread-like structures creating invisible networks that connect widely separated organisms. Some deep-sea mushrooms fruit only once in decades, producing spores that drift with deep currents to establish new colonies on distant patches of suitable seafloor. The fungal networks represent some of the oldest continuous organisms, isms in the deep sea, their underground structures potentially persisting for millennia as they slowly process the organic matter that rains down from above. Pressure gardens bloom in the deepest trenches, where the extreme conditions create unique ecosystems adapted to pressures that would instantly crush surface-dwelling organisms. These communities exist in a world where water behaves more like a solid than a liquid, where the pressure is so intense that it affects the basic chemistry of life processes. The organisms in these pressure gardens have evolved biochemistry that not only tolerates, but requires the extreme conditions. Their cellular processes optimized for pressures found nowhere else on Earth. The gardens represent the absolute limit of life on our planet, thriving in conditions that approach those found in the interiors of other worlds. Their existence expands our understanding of life's possibilities and suggests that similar organisms Anisms might exist in the high-pressure oceans beneath the ice of distant moons. Acoustic fossils preserve ancient sounds in the layered sediments of the deep ocean floor, where the vibrations of long-extinct creatures may still echo in the compressed particles that accumulated around their remains. These sound shadows are created when dense organic matter alters the acoustic properties of settling sediments, creating subtle variations in how sound waves propagate through different layers. Deep-sea archaeologists of the future might learn to read these acoustic records, extracting the calls and songs of ancient marine life from sediment cores pulled from the deepest basins. The ocean floor becomes a vast acoustic library where the voices of prehistoric seas wait silently in the compressed time of geological layers, their stories written in the language of sound waves and sediment grains. Bacterial highways create invisible roads across the abyssal plains, where chemical trails left by migrating microbes guide other organisms through the featureless darkness. These molecular pathways persist for weeks or months in the stable conditions of the deep sea, creating navigation networks that connect distant feeding grounds and breeding sites. The highways are maintained by the constant traffic of organisms following the chemical signals, their passage refreshing and strengthening the trails for future travelers. Deep-sea creatures learn these invisible roads like migrating birds learn flyways, following ancient pathways that have guided movement across the ocean floor for thousands of years. The bacterial highways represent a form of biological infrastructure, invisible roads that organize and direct the flow of life across the vast emptiness of the deep sea. Time capsules drift through the deep ocean in the form of ancient organic matter that has remained unchanged for millions of years in the cold, dark water. These molecular fossils carry within them the chemical signatures of prehistoric ecosystems, preserving samples of ancient atmospheres and vanished food webs in their complex organic structures. The capsules are occasionally disturbed by deep currents or geological activity, releasing their ancient contents into modern ecosystems where they provide glimpses into life as it existed in earlier eras. Some deep-sea organisms have evolved to exploit these time capsules. They're specialized enzymes capable of breaking down organic molecules that have been stable for geological periods. The ancient matter represents a form of chemical archaeology, allowing the deep sea to sample and digest its own history. Liquid crystals form in the deep ocean, where extreme pressure and specific mineral compositions create water with unusual optical properties that bend and focus light in ways that don't occur at the surface. These regions of structured water can concentrate the faint B, creating natural bioluminescence of deep-sea organism senses that amplify biological light and make it visible across greater distances. The liquid crystals form temporary structures that shift and change with currents and pressure variations, creating moving patterns of enhanced visibility that deep-sea creatures may use for communication and navigation. The phenomenon represents an intersection of physics and biology, where the properties of water itself become part of the deep sea's optical environment, adding another layer of complexity to an already mysterious realm. The deep ocean continues its patient work in rhythms older than continents, its processes unfolding with the steady persistence of geological time. In the bacterial gardens and glass cathedrals, in the chemical highways and acoustic fossils, the sea holds its ancient wisdom in forms too vast and slow for surface minds to fully comprehend. The deepest waters ask nothing of the world above, following their own timeless cycles in the eternal darkness below. Abyssal meditation chambers form in the deepest parts of the ocean, where currents slow to an almost perfect stillness, creating pockets of water so calm they seem to exist outside of time itself. These liquid sanctuaries develop where multiple deep currents converge and cancel each other's motion, leaving behind zones of profound tranquility that can persist for years without disturbance. The water in these chambers is so still that individual particles may remain suspended in the same position for months, creating three-dimensional sculptures of marine snow that hang motionless in the darkness. Deep-sea creatures discover these meditation chambers and use them as resting places. Their movements so gentle, they barely disturb the perfect calm. The chambers represent the ocean's deepest peace, places where the constant motion of the sea pauses to breathe. Whisper currents carry messages through the deep ocean in flows so gentle they can barely be detected by the most sensitive instruments. These subtle streams of water move like liquid sighs through the abyssal depths, their passage marked only by the faintest chemical traces and temperature variations. Marine organisms have learned to read these whisper currents like a secret language, following their nearly imperceptible flow to find food sources and mating grounds scattered across the vast darkness. The currents carry information across entire ocean basins at speeds measured in meters per day, their messages taking decades to travel from one side of the Pacific to the other. In the whisper currents, the ocean speaks to itself in voices too soft for human ears to hear. Sediment gardens bloom on the abyssal plains, where fine particles settle into patterns that create microhabitats for specialized communities of microscopic life. These gardens form over thousands of years as different types of sediment accumulate in subtle variations across the seafloor, creating patches of clay, silt, and organic matter that support distinct bacterial ecosystems. Each type of sediment hosts its own community of microorganisms, their metabolic processes slowly altering the chemistry of their environment and creating gradients of nutrients that attract larger creatures. The gardens are invisible to the naked eye, but teem with activity as billions of microscopic organisms process nutrients and exchange gases in cycles that mirror the seasonal rhythms of terrestrial ecosystems. Liquid archaeology preserves the history of the deep sea in layers of water that carry dissolved remnants of ancient ecosystems. Different water masses retain their chemical signatures for decades as they flow through the deep ocean basins, carrying with them the dissolved remains of organisms that lived and died in distant seas. Scientists can read these liquid records like pages in a book, identifying water that originated near melting glaciers, around hydrothermal vents, or in regions of high biological productivity. The water itself becomes a form of memory, preserving evidence of environmental conditions that existed when it first sank toward the depths. Each sample tells a story of the ocean's past, written in the language of dissolved minerals and trace gases. Thermal oases develop around underwater hot springs, where the Earth's internal heat creates pockets of warmth that support tropical ecosystems in the polar depths. These warm water refugia can persist for centuries around long-lived geothermal features. Their stable temperatures allowing species from warmer climates to survive in regions that would otherwise be too cold to support them. The oases act like underwater islands, isolated populations of warm water organisms surrounded by vast expanses of frigid, deep water. Some thermal oases have been stable for so long that they have allowed evolution to occur in isolation, creating endemic species found nowhere else in the ocean. The warm springs create bridges between different climate zones, allowing tropical marine life to exist in the eternal winter of the deep sea. And so we drift to the end of our gentle descent into the ocean's deepest secrets. We've traveled through liquid libraries where ancient sounds echo across basins, watched marine snow fall upward in slow motion, and listened to the planet's quiet breathing in currents that have flowed for millions of years. In bacterial gardens and glass cathedrals, in thermal oases and whisper currents, the sea continues its patient work, asking nothing of the surface world, but offering everything to those who pause to listen. These depths teach us that the most profound processes happen slowly, quietly, beyond the reach of hurried minds. As you rest now, may you carry with you the ocean's gentle rhythm, its endless patience, and its quiet reminder that even in the deepest darkness, life finds ways to flow, nourish, and shine.